Hey everyone, Houston Math Prep here to talk you through logarithmic differentiation. There are two main types of derivatives where using properties of logs, this logarithmic differentiation method we're going to go through is useful. The first type of problem is when you're trying to take the derivative of a statement that has many products and quotients and powers all mixed into it. Maybe you have, a product rule and a quotient rule and a chain rule, or a mixture of a bunch of those all in one problem, and it looks really complicated to do. Logarithmic differentiation, these properties of exponents are going to help us do those. The other type of problem we'll work through in this video is taking the derivative of some type of expression where you have a variable in both the base and the exponent of what you're trying to take the derivative of. Let's look here at an example that is a monster. We have derivative with respect to x of the quantity x plus 1 all squared times the quantity x minus 3, all of that divided by the quantity x plus 4 all cubed. So think about what we have. This is a really terrible quotient rule. We have a quotient rule, and when we take the derivative of the top as part of our quotient rule, it's also a product rule inside of our quotient rule. And each of these is not just x, so we also have chain rules inside of every piece of our derivative involving the quotient and the product rule, right? So there's lots of layers here. So what we're going to do is avoid product, quotient, chain, oh my rules, right? That's a lot of stuff. We're actually going to just start by letting y equal this expression that we have. So y is equal to x plus 1 squared, x minus 3, all over x plus 4 quantity cubed. And what we're going to do is take the natural log of both sides. Okay, now that's going to help us because properties of logs are going to allow us to break this up into different pieces, and then each piece is going to be a simpler expression to do the derivative of. So we'll go ahead and keep our ln of y here. And remember, properties of logs say if I have a product, that becomes add if I split it up into separate logs. And if I have a quotient, if I divide by something, then that becomes subtract when I split it up into separate logs. So I'm going to break this all up into separate logarithms. I'm going to say the first one is x plus 1 all squared inside of a log. This is times this next thing. So we have plus ln of x minus 3. And since it's divide by this inside the log, that would make that minus ln of x plus 4 all cubed. Okay, so we've broken this up. We no longer have to deal with any sort of quotient rule, which is nice. And now what I'm going to do is actually move these powers out front as well. We can do that. So I'm going to go ahead and say up here, we'll say ln of y is equal to, move this 2 to the front, and I'm going to move this 3 to the front. So this will be 2 ln of x plus 1 plus, we'll leave that ln of x minus 3. And then this last one here, we'll say minus 3 ln of x plus 4. Okay, so we've got an equivalent expression to this over here. We just broke it up into a bunch of pieces. And now this is a good time, I think, to take the derivative. So from here, what we will do is we will take the derivative with respect to x, just the whole thing. So we'll have a little bit of implicit differentiation here, especially on this left side. Right? So we'll go ahead and say the derivative of ln of something, remember, is 1 over that something, and then times the chain rule when we need it. So the derivative of ln y is going to be 1 over y. And now the derivative of the inside will also give us times dy dx. Okay, so that's our left side. So think about, we have over here just a bunch of log rules, right? 1 over. We're taking the reciprocals of things. So the derivative of 2 ln of x plus 1, so first of all, keep the 2. That's just a constant multiple. And then the derivative of ln of x plus 1 will just be 1 over x plus 1, right? So we'll get 2 over x plus 1 for this one. Chain rule, the derivative of the inside would just be 1, right? The derivative is 1 here, so nothing to multiply by there. Plus, let's move on to the next term. Derivative of ln of x minus 3 would be 1 over that thing, 1 over x minus 3. Chain rule says times the derivative of the inside, but the derivative of the inside is again 1. We have a 1x here. So we'll move on to the next one. Minus, let's go ahead and keep our constant multiple of 3. And the derivative of ln of x plus 4 would be 1 over x plus 4. The derivative of the inside for the chain rule would again be 1 for this one, so times 1 won't change anything there. So we get this nice thing where just everything is an ln rule, every term that we hit, same rule, just being careful to make sure we're careful about our chain rule. Now if I want to get this derivative term by itself, then I just go ahead and multiply everything by y, right? So I will get dy dx is equal to 2 over x plus 1 over x minus 3 minus 3 over x plus 4, and all of that is going to be times y. And so we're almost finished. We really are finished, but I think it's nicer to say what we had before. If you remember, right before I took the ln of both sides here, at the beginning of this problem, we said we were going to let y equal this, right? So what I actually then need to go back and do is replace my y with the original statement that I had when I began, right? So my dy dx, going to compact just a little bit here. So that's going to be what we got on the right side. You'll notice times what we started with, right? So we get 2 over x plus 1 over x minus 3 over x plus 4. And then all of that is going to be times the x plus 1 all squared, x minus 3 all over x plus 4 cubed. And now you're getting to the point in your calculus where I think we want to excuse you from processes like getting a common denominator. Okay, I'm a firm believer that once we get to this complexity of problem, if it looks reasonable, and though you may get something out of it, if you put in a moderate amount of effort to simplify, you should. But in this case, I think it's going to be a bit gross to try and distribute or do any simplifying or get a common denominator. That would take more time than the actual problem we already just learned to do. So we're going to go ahead and just leave our answer like this here. Let's look at another example here. We'll move through it a bit more quickly this time. So for this one, we have the derivative of x to the 4th times the square root of x squared plus 1, and all of that is over x minus 1 times x plus 2. So again, what we'll do here is we'll go ahead and have y equal all of this stuff. So y equals x to the 4 square root x squared plus 1 all over x minus 1 x plus 2. And then remember what we do. We go ahead and take the natural log of both sides. I'm going to do it in pink here so we can remember what y equaled when we get to the end. So we take the natural log of both sides, and now we use our properties of logs to help us break everything up. Okay, so I'm going to do this, I'm going to do this all in one shot here. So I've got these on the top being positive, and these are really divide on the bottom, so these will be negative log terms when we split it up. And notice I've got some powers here, okay? So I have ln of x to the 4, but I'm going to go ahead and move that 4 to the front. So that first term is really going to be 4 ln of x plus, now this root, remember roots are 1/2 power, right? So that's like saying everything in the log to the 1/2 power. So moving that 1/2 power to the front, we'll actually say 1/2 ln of x squared plus 1. Now these are subtract on the bottom, so this will be minus ln of x minus 1 minus ln of x plus 2. Okay, so we have all of that. And now let's go ahead and from here just do our implicit derivative. So derivative of ln y, remember, is going to be 1 over y. Chain rule gives us times dy dx. Now here, 4 times ln x, derivative of that, we'd keep the 4. Derivative of ln x is just 1 over x, so we get 4 over x here. Plus, here we get a half. Now with this one, ln of x squared plus 1, derivative of that would be 1 over that, so 1 over x squared plus 1. Don't forget your chain rule though, times the derivative of the inside means we would also get a 2x for that term there. Over here we have minus, so minus derivative of ln x minus 1 would be 1 over x minus 1. The chain rule for the inside, the derivative is 1, so we don't need to include anything additional there. And a similar thing here, right? We'll get minus derivative of ln of that is 1 over that. And the chain rule, again, the derivative is 1 here, so we'll go ahead and keep all of that. I'm going to go ahead and scroll down and keep working. So let's go ahead and clean this up. We'll say 1 over y dy dx. You might have noticed we're going to get that, right? On the left side, we'll have ln of y, and then when we take the derivative, we'll get 1 over y dy dx. That's always going to happen here as long as we have y equals. on the left side. So here we'll have 4 over x plus, now notice the 2 here is going to reduce the 2 on the bottom from the 1/2. So we'll actually get x over x squared plus 1 minus 1 over x minus 1. Can you imagine getting a common denominator with this and trying to simplify this? Isn't that gross? That'd be gross. Okay, so now we just need to solve dy dx by multiplying both sides by y. And remember, when we do that, we're going to go ahead and replace the y with what we started with anyway. So I'm going to go ahead and do that all in one step here to save a bunch of writing. Some of these are long to write, yeah. So we would get 4 over x plus x over x squared plus 1 minus 1 over x minus 1 minus 1 over x plus 2. And then times the y here is times x to the 4 square root x squared plus 1 over x minus 1 x plus 2. And that's our y that we replaced with from the very beginning here, right? Y equals. And that is our nice, long, complicated answer for this problem. But it did allow us to skip the quotient rule, which has chain rules inside of product rules as part of the quotient rule. Doing this, I think, with quotient and product and chain rules without doing logarithmic differentiation would take probably at least 3 times as long as what we did here. For logarithmic differentiation, before we do the other type of problem, we'll go ahead and give you an outline for it. So you want to make sure you get y equals. You'll take the natural log of both sides, so you'll have ln y on the left side and ln of all your stuff on the right side. You use your properties of logs to break up all the stuff on the right side into separate logs. Then you'll go ahead and take the derivative with respect to x straight across from left to right to implicit differentiation. Remember, we always ended up with a 1 over y dy dx on the left side, so you'll just need to multiply that y to the other side, and then you'll replace it with the original statement that you called y at the beginning of the problem. Let's take a look at the other type of problem where this is really handy. So we have the derivative with respect to x of x to the x. And this looks really short and simple, and it is. It's just a statement that says x to the x. The problem is we haven't learned any sort of method to figure out the derivative of something that is a base that has a variable in it to something that has a power with a variable in it. We've done polynomials that are things like x cubed, and we've done exponentials that are things like 3 to the x, but we haven't done anything where it's x to the x. So we have a variable in the base and the exponent. We'll use this same idea of logarithmic differentiation when you have that. So our first step, remember, is to let y equal whatever we're trying to take the derivative of. So here y equals x to the x. We're going to go through our outline. So the next thing is to take the ln of both sides. So we end up with ln of y is equal to ln of x to the x. And remember, the reason we do that is so that we can move the exponent out for something like this. We want to make this simpler. So the way we break this one up is actually just to move the power x to the front. We say x times ln x. And now when we do the derivative of this, so if we say ln y equals x times ln x, and we do the derivative, which is implicit, right, because we have ln y on the left, what I really end up with is just a small product rule on the right, so that's not so bad. So let's do this. The derivative of ln y is 1 over y, and we know we get times dy dx from the chain rule. And on the right side, I'll think of this as my f, and ln of x as my g, and so I'll have f prime g as the first part of my product rule. F prime would be 1. G is just ln of x, plus, now we'll have fg prime, so f is x, and g prime, the derivative of ln x, would just be 1 over x. And we'll do a little bit of simplifying over here. So I have 1 over y dy dx equal to 1 times ln x, that'll just be ln x, and x times 1 over x, well, that's just 1, right? And remember our last step, right? Now we multiply this y to the other side, and we'll replace it with the original. We said that y was x to the x before, so when I multiply y to the other side, then we'll get that dy dx, our derivative we were looking for, is actually ln of x plus 1, and replacing our y, we get times x to the x for this. Let's look at one last example in our video here. We have the derivative of x to the sine x. So we'll go ahead and use our outline, think y equals x to the sine x. Remember now we take the natural log of both sides, so we'll get ln of y is equal to ln of x to the sine x. And with these, the idea is to get this exponent out front of the log. So we'll think of this as ln y equals sine of x times ln of x, just using properties of logs there. And now we'll take the derivative, right? So taking the derivative with respect to x of our entire equation that we have now, you can see we get a pretty easy product rule on the other side. Nothing too scary. So derivative of ln y we know is 1 over y. Chain rule gives us dy dx equal to, my f is sine x and my g is ln x for product rule. So f prime g, f prime would be cosine of x times g, which is just ln x, plus fg prime, so that would be sine x, and the derivative of ln x would be 1 over x here. So we'll go ahead and say 1 over y dy dx is equal to, let's call this cosine x ln x, plus here maybe if I write this as sine of x over x, we could do that. And now remember what we need to do is get rid of the 1 over y, so we'll multiply both sides by y and get rid of 1 over y there. So we'll get dy dx is then equal to, we get cosine x ln x plus sine x over x. And let's go ahead and replace our y. So y was x to the sine x, so we'll go ahead and say times x to the sine x. Okay, everyone, hopefully it's clear after working a few with us how to do your logarithmic differentiation, both with really complicated looking rational problems and with just something simple where we have a variable in both the base and the exponent. Thanks for watching. We'll see you in the next video.